Thank you so much for inviting me. This is my first time giving this talk. It's based on an upcoming survey we're writing with David, Neelin, Hui Su, and others. But I'm going to mostly focus on published or very recent work so that it's all new, or most of it is hopefully new for you. So my name is Tom Beucler, and I lead a group at exploring the intersection of atmospheric physics and AI. I think back in 2021, we were the first group officially doing this. Now it's much more common. So I'm especially interested in the interplay between the knowledge we have about a climate system and the troves of data we have, observational data, high fidelity simulation data, and the machine learning algorithms we can use to learn more from data. And so I'm a professor of environmental data science, and we work both on Earth system modeling, particularly focusing on improving uncertain parts of our Earth system models, so parametrizations mostly, and then especially with our new Expertise Center for Climate Extremes, we think a lot about how AI can help us better forecast the weather, in particular extreme weather. So we work a lot on forecasting, post-processing, and downscaling.
Sorry, what's the picture on the right? Is it water or is it snow?
It's water. I think it's actually back from when I was sitting at Scripps. It's a dam breaking.
Yeah.
It's up near Sacramento.
Yeah.
Orville Dam, I think.
Exactly, back from when I was at CW3 for a little bit. Okay. And the motivation for this talk, AI Pathways from Weather to Climate, is the incredible success that artificial intelligence has had at forecasting weather. I'm really grateful that Kathy already introduced so much of the basics. And indeed, the reason why it's so appropriate to frame weather forecasting as a data-driven problem is that you can cleanly frame it as an initial conditions autoregressive problem. And so, well, assuming you have a functional data assimilation system, but I'm grateful, I think Noah's going to speak and other people will dive more into it. You can assume you know the state of the atmosphere now, and then your goal is simply to autoregressively predict the next state. And so this can be mathematically framed quite simply as an initial conditions problem. It can be framed simply. It's not necessarily simple to solve, but at least it's very tractable. And so this has allowed a lot of progress, notably thanks to the availability of public data sets, such as the Era 5 meteorological reanalysis, as Kathy mentioned. And this is one of the early, it was a couple of years ago, success pictures of GraphCast, where 10 days ahead, it was able to make a forecast rivaling our best traditional forecasting system, which is HRES from ECMWF. So at least back then, it was an incredible success of course, there's a lot of caveats. It's a deterministic forecast, so it's a really good conditional mean estimator. But in any case, it was really impressive because once trained, these run on one GPU. You can even run them on CPU by pushing things a little bit. And you're rivaling weather forecasting systems that use thousands of CPUs. And I really like this chart from Stefan Hoyer and Stefan Rask from Google, which shows root mean squared error scale compared to our best traditional forecasting system from the European Center for Medium-Range Weather Forecasting. And we're focusing here on mid-level geopotential height forecasts. And you can see, we're talking about diversity of architectures. I would argue maybe there was a tiny bit more diversity initially as people were trying things out. So big shout out to Jonathan Wayne, who as a grad student developed some of the first architectures with Del Duran. And eventually, and especially I think thanks to Weather Bench, Stefan Rask making the data and performance metrics clear for everyone really helped bolster progress. We've had, since a couple of years, systems that outperform in as based on a deterministic skill measure, some of our top forecasting system. And here we can see there's an explosion of models, especially as the data sets, the tool, the performance metrics become more and more available. And the question, and this all...
I don't say, what is the performance metric? I mean, how can it be more than 100%, or what's going on here?
So it's not exactly a skill score, but it's based on the root mean squared error, and you compare it to the root mean squared error of the HRES forecasting system. 100 is when your root mean squared error is as good as that system, and then when it gets better, you're going to go above 100. So it's a little bit like this trick where you take any performance metric and you do 1 minus performance metrics divided by baseline performance metrics. So it's just a simple rescaling. And then motivated, we were at a workshop in Hong Kong years ago, and then we got into this discussion of what separates AI for weather and AI for climate, because we have all the success in AI for weather, and a lot of teams and groups are hoping to translate some of that success to climate. And one of the discussions ended up around the fact that they're separated by more than just lead time. Of course, AI for weather can be framed as an initial condition problem, where based on an initial state, we're going to predict a future state. The reason it's so tractable is because it's a paired problem mathematically, so you can have a well-defined measure of success. Meanwhile, climate is a boundary conditions problem. What you're trying to do is predict the full time series response of a system driven by boundary conditions. But then there's an additional element which I think makes it so different, is that climate scientists are traditionally interested in answering fundamental questions about counterfactuals. And so I think that's where there's a real barrier, because you're going to want to answer questions such as, what happens if I force a climate system with aerosols and greenhouse gases that I've never seen before, emitted from a country that has maybe never emitted before? And so there's this whole aspect of causality and counterfactuals that separates it a bit more than just an initial versus boundary conditions problem. But where they're unified and is that they both at least share a huge challenge, which is a challenge in applied machine learning in general, which is the out-of-distribution challenge. That is, there's no reason for your data-driven algorithms to do well on data that's outside of their training distribution unless you make additional assumptions or tricks, etc. But there's no reasons a priori. And this challenge can be seen both in AI for weather applications. So this is a nice paper from Pedram, and it was led by Sun, showing that if you take ForecastNet and you remove the most intense tropical cyclones from the training set, then you start doing really poorly as the most intense tropical cyclones. So there's another one in Switzerland, where I'm not the co-author, where they showed that for the most extreme heat waves or cold air outbreaks, traditional numerical weather prediction still outperforms AI weather predictions. The challenge is a bit more acute in climate applications. So this is from a paper I wrote where we design machine learning parameterizations of convection, and we have fun training these parameterization in an aquaplanet climate, and then we test them in an aquaplanet that's whose surface is 8 Kelvin warmer, and then we get these really nice dramatic failure by an order 10. So this is nice because you fully break the machine learning models. And this is a clean example out of an out-of-distribution challenge. And so I'm going to use this unifying challenge to present some of our recent research. Once we write the survey, it's going to be a lot more than that, and it will group everyone together, but I'm going to focus on research from that I'm part of, since I'm guessing this is what's interesting. I came all the way from Switzerland. I felt a bit sick, but I'm really excited to be here this week with you and learn about what everyone is doing here. And so for the out-of-distribution weather challenge, I'm going to focus on the work on tropical cyclone forecasting, because until recently, and that's currently changing, so that's the frontier, we're excited about this. It's been really hard to forecast extremes, and several groups around the world are all working on this issue, and it seems that it's a solvable issue from multiple angles. So I'll present you our solution to it and how that connects to other efforts that we've benchmarked as well. And then for the out-of-distribution climate problem, I'll talk about our efforts collaborative efforts. So these are collaboration with the DLR group led by Veronika Ehring, but also I'm going to mention my a paper with Tapio, not for too long because I think Tapio is going to speak as well, so you'll get to hear plenty about Klima, which is a fantastic example of online parametrization learning. I'll get to it in a second. And I think this is one of the most promising solutions we have to the out-of-distribution climate problem. There may be many other, and I'll mention them, but I think the hybrid modeling approach, for now, is a good compromise. And finally, because these are more experimental results that I found for the survey, and because I'm sure some of you will have strong opinions on them, I can already guess, I want to present you these new, very, very simple results just for discussion and to see what happens when we think about, okay, what are we really gaining when we're using AI? Are we really getting the scaling that we want, this acceleration that we promised? So I'll start with the weather example, and to make it a little more dramatic, I'll start with a particular case study, Hurricane Otis, which hit Mexico in October 2023. It was the city of Acapulco, and what made it so special is that it underwent what we call rapid intensification. So its surface wind speed increased much more than the statistical average. And importantly, it did that right before making landfall. And so that was missed by all forecasting models, not just the traditional one, but also the new AI models that were out there. So it's a really nice case because it's a challenging case for all the models that were out there in October 2023. So I've used, to show it nicely, and now we have a similar internal tools, but I really love this tool that Google put out called Weather Lab. You can look on Weather Lab at past tropical cyclones and look how well different models did. And so here it's a forecast issued on Monday, October 23rd. So you can see a little bit before the hurricane made landfall. And the truth, so max wind speed and minimum sea level pressure are the black lines. And what you can see is that if we look at the two models that I'm showing here, and so here I'm showing GraphCast in purple, and I'm showing ECMWF HRES in yellow. They both, I mean, they failed miserably to predict the intensification, and by a lot, right? I mean, it's a very clear bust. And yes?
Just wanted to mention there that, going back to your comment about weather being in an initial conditions problem and then something solvable, in this particular case, the hurricane hunters were not able to fly out because the planes were not working. Not surprisingly, they're not getting funded as much as they should. And so they were not able to see Otis firsthand during this process. And I think they weren't able to get the initial conditions that you would use to give a better forecast.
There's that, and on top of that, the sea surface temperatures were warmer than the climatological, and so like we were missing a ton of observations. So it's a mixed, but I think the positive results, you're right, one has to be careful. It's a mix of modeling mistake and data assimilation problems.
I think it's more modeling in this case, but I just wanted to point that out because I remember so clearly, and I was very frustrated about that.
I mean, in all cases, these models are not going to get the intensity right. They're going to underestimate it, but maybe they wouldn't have underestimated by that much. I did not decompose the error in this case, so I will not exactly answer that, but I think that's really interesting. And also it shows that it's a mix, like we also have to work a lot on data assimilation. I think there's a lot of talks this week about this topic. What's interesting, though, is the press immediately jumped on it, right? AI weather forecasting cannot replace humans yet. Little ominous yet. And so it's a case that I thought was really timely. And it's also timely because it's right as a probabilistic AI weather prediction system started being developed. And so since we, in an applied math institute, I thought I would formalize things a tiny bit. So in the deterministic case, things can be written very clearly. In most cases, models actually are integrating using a Euler scheme, and they kind of learn to be stable with the Euler scheme. So it's as simple as the state at the next time step is the state at the previous time step plus a learned function. It's a Markov process of order 1, sometimes order 2, like GraphCast or AIFS, but it doesn't really go above 2. Meanwhile, if you know that there's inherent uncertainty in the atmosphere, it comes from different sources, but the most obvious one is chaos. Then you know that you should describe your forecast probabilistically, and then you can frame it as a member I of an ensemble forecast is the previous state plus an increment, and that increment is sampled from a learned distribution. So here I'm putting the little theta parameter to indicate that it's learned, of the state condition on, again, if you take the current state, it's order 1, then the previous state, order 2, etc. And so what's interesting is that that hurricane happened right before the probabilistic AI weather model came out. So right before GenCast, way before AIFS, CRPS, way before, and I want to point this out because it's going to be important, FGN, which is currently possibly the best probabilistic AI forecasting system we have. And an issue, and also why we've developed benchmarking efforts, is that if you look at these papers, it's a bit tricky, because until recently, what they did is they only evaluated the tropical cyclone forecasts on the tracks they actually predicted. So it's a bit artificial in the sense that they will just not even consider what they didn't predict. This is until recently. Things are changing this year, and that's quite exciting. Yeah,
quick question. Can you come back to the model slide before?
Like this, this one would work?
The one with the Euler scheme?
Yeah.
I think.
So this is
no, just the math, the one-liner of math. Yeah. So I would argue slightly differently for diffusion models, because since you have the diffusion process, which corresponds to integrating an SDE that takes the prior of the previous state of the atmosphere, one could argue that the model might be able to come up with integration schemes that are much higher order than just this one, which could be seen as a way to why they have so much more precision.
But in terms of information, they're still given the same information, no? If you see it from the...
Yes, but you could argue that there is more autoregressive steps. That's instead of just one.
Could you just see it as a change in loss function and you're still restricting the information the same way? I mean, I guess maybe...
Yeah, no,
For me, I mostly see diffusion model as a fundamental change in the loss function more than the...
No, I don't fully agree with that. No.
I know GenCast in particular learned something akin to the top. I think they said for everything except precipitation, they learned the delta.
Yeah.
It denoises the delta between t-1 and t, or t and t+1.
I think my counter argument to this is just that if you run the model, all you really need is, practically, you only need the current and the previous time step. And so I think from an information flow perspective, but I agree with you, and let's talk about it afterwards.
Yeah.
Okay, and so our idea, a couple of years ago, so it was right after Pengu, ForecastNet 2, etc., was starting to be quite available and possible to run, at least in an academic lab context, was to say, okay, we're not going to get the resolution to understand TC intensity, which is the maximum of the surface wind speed, so you require pretty high resolution. So there's a scale mismatch that we're not going to be able to fill until much later when we have incredibly gridded data set, if we ever get there. And so we're just going to directly target our best observations using a post-processing approach. And so mathematically, you can see it like this. Now you have an auxiliary task where you have an observations, and you're just going to target it, and you're going to sample it from a learned distribution where you condition this distribution on the forecast state. And what motivated us to do that was a preliminary study where we evaluated different neural weather model or AI weather prediction models that is GraphCast, Pengu, and ForecastNet v2. And we especially focused on convective parameters. That was back in 2023, 2024. And we showed that at least from the perspective of CAPE and deep layer shear, which are important if you're interested in severe convective events, these were on par, if not better than IFS, at least back then for Pengu and GraphCast. And so then our idea was, okay, we're not going to be able to directly predict the high-resolution surface winds field of the tropical cyclone, but what these AI weather prediction models give us is a forecast, a core scale environment, a 0.25-degree environment that contains information that we can then use to recover the observations we're interested in. So the idea is we start from, and just to be a bit cleaner, in this case, we're going to frame the problem of tropical cyclone forecasting as a regression with known initial condition. So we're going to assume we have an initial disturbance, which is usually how they're forecast in practice, where you know the initial position and the initial intensity, and then we're going to ask ourselves how does it evolve in time, and can we use these advances in AI weather prediction to do medium-range weather forecasting of tropical cyclone track. What these models are okay at doing, but importantly intensity, which these models are very poor at doing just because Area 5 doesn't get the intensity of tropical cyclones. And so the way we frame the problem is quite, is based on these AI weather prediction model. And I think there's there's also efforts in AIES in post-processing these neural weather models that were in parallel for convective classification problems. So we're not the only ones who came up with these ideas. And so the idea is you take a neural weather model and you're going to do the forecast of the course environment using that neural weather model. So this is a model that will allow you to advance in time. And then in the most naive case, and that's a bit different from what was published because you could take the full time series, but here we wanted to do something that was really cheap so that it would fit on one GPU, and our idea was, can we democratize the forecasting of tropical cyclones so that the whole thing fits on one tiny GPU? So what we do is we just forecast the course environment, 0.25 degrees, and then we clip the region around the initial position of the disturbance, allowing a large enough region so that, based on past statistics, the tropical cyclone wouldn't go out of the domain. And then we just make a prediction on the masked field. We frame it as a distributional regression problem. And so in the deterministic case, it's simple. We just minimize the squared error between, for example, the observed intensity and what a model predicts. But the advantage of distributional regression is it's very simple to extend it to the probabilistic case. So in this case, we found that a conditional normal distribution was good enough. And so in that case, you can calculate the closed form for the continuous rank probability score that's been established for 10, 15 years. And it's all based on the PDF and the CDF of the normal distribution. And because you have a closed form, it's relatively cheap and feasible to optimize. And then we can look at how it does on actual forecasts. So that was a tool that was developed internally by a really talented civil servant, a master's student. And so what he was able to show for Otis is that most models do very poorly, except the new Google model called FNV3. And that's a really impressive model because it's operational already. It's not public. I think what you can gather from its performance and how it's designed is that it runs on this FGN model, which is state-of-the-art generative. It's better than GenCast. And then it has been either fine-tuned or as an auxiliary task, they targeted IB tracks, so observational data. Otherwise, it would never do so well on a tropical cyclone intensity forecast. But so we benchmark it, and it's really impressive, really good. What we're happy with is a really simple model, which we didn't test it in operational conditions. We don't have a full DeepMind team at the University of Lausanne. But just as a simple distributional regression approach with just a conditional normal distribution, can get the intensity to a reasonable amount. That's true for a special case, but that's also true when we test it on an entire year of cases. So we use 2023 as a test case. We confirm with DeepMind that with the data they put out, they also didn't use it as training years. And so we have this benchmark dataset called TC-Bench that we've been working on for 2-3 years now, that we just put out on archive, where we compare all the models, and they all do terribly, except if you target IB tracks specifically, which FNV does, and our simple post-processing approach does. Our post-processing approach is not model-specific, so you could do that on any AI weather prediction models. We found that it worked really well on Pengu, and Pengu is really fast to run. But since we're Europe-based, we're going to keep working on AIFS, because it's publicly maintained, and we all encourage to use it, and it does really well for precipitation-related processes. And so there's more to come. But I think the good news, and at some point Google will release the actual paper explaining what they did, and that's going to be really interesting for the community. Yeah.
I don't mean to interrupt you.
No, go ahead, Noah.
So why are they all worse at the initial? Is that the initial time, the 12-hour time versus 24? It seems like they're all really bad at the initial condition, and then they get better. Do you have an understanding of that?
Sorry. Again, why they're doing so poorly at the initial time?
Yeah, so typically 12 hours in, they're all red, and they get blue for 24. Like FN33 is blue for 24, and so on. So it seems like they're.
These are all medium-range weather forecasting model. I think it's because of the way we frame the problem. I think it's because when we look at this problem, we make a strong assumption where we know with the initial disturbances. So that gives you a ton of information at the beginning. My guess is, these don't have access to that information. And so in that sense, I think it's a nice framing because it's closer to what's done in reality. I'm not claiming that here, this should be run operationally right away. There's a huge data assimilation challenge, which is to get that initial information in time. Clearly, FNV got it in some way. So they managed to find not a perfect, but at least a partial solution to it. And since they run operationally, they don't have that knowledge of IB tracks. So my guess is they get it from the IFS initial conditions. But that's, I don't know. People who work a lot on data assimilation, working on, what it tells you is that the knowledge of that information, the more you can get it right for that particular problem, the better you would do. It doesn't mean that we do amazing at short lead time. That's not how it would interpret it. This is a proof of concept that this could be really promising for medium range weather forecasting, but for nowcasting, it's a completely different problem, right? So, I don't know. Does that answer the question, or? Basically, we make a strong assumption that in practice, you wouldn't have so much information at very, very short lead times. That's a short answer.
It just seems like an obvious way to improve the initial state estimate. You'll get better. You should result in.
Yeah, so I wouldn't. You're right that maybe we should write a huge. That's a good point. I think we should write a huge caveat that assumption of knowing where the initial disturbance is and how intense it is will overestimate probably the current data assimilation capabilities that we have for the very short lead times. I think that's a caveat that you're talking about.
And your takeaway is basically that FN33 just kind of creates things that a track detection algorithm can identify as tropical cyclones, but you can do the same thing by post-processing Pengu.
Yeah, and they run their own tracking, so they already give you intensity and track. It's on Weather Lab, you can download it. So they already did that work incredibly well. They clearly targeted IB tracks. Now the exact details are not known, we just know that it's FGN based. Yeah.
My colleague Michael Fisher can tell me if this makes sense or not, but I think this is a cyclogenesis problem, or at least a big part of it. When you have a tropical storm and you first start saying, okay, we're going to predict from when we've named the storm, the next 12 hours always have much lower predictability than further on when it actually does become a hurricane, right? So there's like a survivorship bias here, right? If the tropical storm if it doesn't actually become a hurricane, it's not going to go into this data. If it does become a hurricane, then it will, and you will have a high level of error. Even if you weren't doing AI, there's going to be a high level of error in the first couple of days of cyclogenesis.
Yeah, I mean, that's true. In addition to the fact that here we're not doing, there are, on top of that, data assimilation challenges. So there's this survivorship bias, there's the fact that tropical cyclogenesis is really tricky, and on top of that, there's the fact that you need to be mindful of the data assimilation, as pointed out Noah. So all three are compounding here. But let me just conclude that section, and then I can switch maybe to climate, and I'm happy to take your question, of course. I think what this shows, and where the field is going, and we've also worked on convective storms, we've been creative in combining machine learning and extreme value theory, is that AI forecasting of weather extremes is possible if appropriate, and by appropriate I mean observational data sources are used as targets, and importantly, appropriate loss functions are used. So you should be penalizing the right variables with the right loss. And I think this is the current frontier. So I think we now saw that, deterministic and probabilistic forecasting, at least at 0.25 degree resolution, was a problem that AI could really help make strides on. I think the forecasting of weather extremes is what's going to come in this year, next, and in the next couple of years. Yeah.
Yeah, so I'm wondering, in my experience, sometimes if you have a model that's trained on extreme events and they do well, but they suck at climatology, and vice versa.
Yeah.
So I was wondering if you, so for this plot that you're showing the statistics of performance for each model for these tropical cyclones, I wonder if you make similar plots, but for testing when there's no tropical cyclone actually formed in the real world, does that show the model's ability to produce false positive tropical cyclone signals? Or
Yeah, and so that is something we take into account in, we debated a lot how to solve that problem, that some models will just not forecast tropical cyclones at all, or fictitious one. And so we have two sets of evaluation scores, one where we focused on the observed one, and one where we focused on only the, one where we penalize the models whenever, for example, they missed one. That's one part of your question, right? How do you handle the fact that some models will create or not create tropical cyclone tracks, and you have to penalize a false positive, etc. The other aspect of your question is really interesting. It's about the fact that it's rare to have a model that's both good at extremes and the climatological mean. Sometimes it's not. Yeah, it's really often a trade-off. And for example, in your loss function, it's always something you think about. One thing, and maybe, I don't know if people are working on that, but one thing we're really thinking of these days is a mixture of experts kind of approach, where you have several experts. So you have AI experts in extreme events, and you have AI experts in the climatological mean. And ideally, your forecasting system, or you should be able to select the one you need, depending on the situation. Again, Google already kind of did that split by doing FGN for the coarse environment and FNV for the TCs. So they made that split explicit, but you could also imagine like a troop of models, and you learn the weights you give to each of them at different times. So I'm going to switch to climate before I'm like hugely over time. I don't know if how much time do I have left, Adam? 10, 15?
13 minutes until Q&A, but there's been questions, so we can go a little into the Q&A time.
I'll try to be quite fast, and you can always ask me questions during the week. So now that we have this success in whether we really thought about a challenge that I don't think anyone will solve in one go, it's something that the community will work on in many decades. In the many decades to come, if I have to guess, because it's a lot harder to create a realistic response to a world we have never seen. And maybe that we will never see, right? We're only going to observe one trajectory. But climate models, if well designed, should be able to give you the response to many different imagined counterfactual trajectories. So this is a bit of a draft of, with David Neelin, we sat down and we said, okay, if you boiled it to the minimum, and you were with someone who was just a brute force AI practitioner, and they knew nothing about climate, what are the most important things a climate model should do? So we just framed it here with different climate variables, phi. One of the main advantages of AI is this ability to create large ensembles to sample statistics. So we're going to index each member using I. And usually what we want to do, at least operationally for climate models, is we want to anticipate the response to different scenario forcings. These can be forcings, this could be a situation where you just prescribe the greenhouse gas concentration and aerosols, or these could be more interactive situation where the model has a dynamic carbon cycle, and then they learn how to handle emissions, etc. So at minima, you should have a way to handle greenhouse gas and aerosols in your climate models so that you can then use these scenarios and get a response. You should probably also have a separate bucket, or at least a way to handle in your model scenarios involving land and water use changes.
So, sorry, the phi's are just variables like T and Q.
Right. It's
They're not probability distributions.
Sorry?
They're not probability distributions.
No, they're just variables here. Yeah. And this is a draft. And then I'll show more general results in other circumstances. But then we thought that maybe the most important thing was to compartmentalize forcings. We thought if there's one thing, maybe one message to give, is that there should be a radiative forcing that's influenced by aerosol and greenhouse gas, and that forcing should only go towards thermodynamic variables. You shouldn't allow it to flow towards any variables directly. You should restrict it so that you have a tractable radiative forcing, and that's just a way to guarantee that at least when exposed to a new scenario that may have never been in the training set, you can at least produce a response.
Does that include indirect effects as well?
Yeah, yes. Yeah. This is just a really general, this is more an argument than a result to anything. And I'm happy to like sit down with whoever wants to challenge it during the week because we're not definite on that. We just said, okay, what's the minimal viable AI climate model? And we thought you should at least compartmentalize the radiative forcing, and you should have a proper handling of land and water use changes. And you should be able to handle complete new counterfactuals. And I think with these prescriptions, you'll be able to clearly rule out, because I think there's a bit of confusion sometimes. People say they do AI for climate, really they're just doing weather. And I think by clearly defining what a minimal viable climate model is, you could rule out some of the more confused efforts so that we can channel it towards, there's also a lot of work still to do in the weather and S2S at the timescales as well. And then, and that's not something I have time to talk about today. We work a lot on that. All the finer scales and what you're able to run at, you can recover partially, at least, using downscaling. Here I'm using downscaling / super resolution. I do distinguish both, and I'm happy to talk more about it. But machine learning has shown a lot of promise for this part as well. And so then it's much cheaper. You can recover the finer scale independently. Now, in that survey, we say, for this out-of-distribution climate challenge, I think the two main strategies that have a clear chance of succeeding are those based on established Earth system models. Because then you have some guarantee of generalizability through the general structure of the climate model to begin with. And I maintain this living review, so I think it's up to date up to December of last year, where I list all these different efforts. It's on GitHub, it's open. And the efforts can be broadly classified into two. emulation, where you emulate an existing climate model. It's in the survey. It's not efforts from my group. I'm not co-author on these papers emulating existing climate models, but some of them are really impressive. A big shout out to ACE2, for example, and the recent Samudra that couples ACE2 to the Samudra model and gets really realistic ENSO as well as sea ice variability. This is an incredible effort. I'm not part of it, I'm just a big fan. You can, it's linked in the review. What I work a lot on is this idea of hybridizing existing established Earth system models, where you start from a model that has dynamical core and a bunch of parameterization, and then you target the parameterizations that you think are most uncertain, could most easily be improved with machine learning. And I'm giving a dynamic seminar in atmospheric science this afternoon at 4 p.m. If you're interested in the details here, I'm just gonna give you the result of many of our efforts where, and that was work led by Arthur Brunner at the DLR doing his PhD thesis, where after distilling neural networks, he was able to find this really simple 10-parameter equation that very faithfully describe cloud cover and outperform the existing cloud cover parameterization used in ICON. And the final result was a mix of a Taylor expansion around the mean thermodynamic state, a really simple term that was able to put the low stratocumulus dex at the right place by using, and that was a feature selection that, so this equation comes from deep learning. So we had a lot of neural networks to non-linearly select features, and then eventually it's a series of papers, we converged to that equation. We found that just the vertical gradient of relative humidity is a really good place to put the stratocumulus dex at the right place on Earth, based on the course environment. And then one last term that takes into account the course.
See the one just off the coast here.
Yes. Yes, the gloom that we experienced during May and June in San Diego, for example. And the last term is really nice because it's able to handle the grid scale mean of liquid and ice. Oops.
Did that cloud parameterization feed back into the main time integrator?
Exactly.
Or was it just diagnosing output from the model? Like, was it one-way or two-way coupled?
It then fed back into the radiation scheme. So then when we...
But not the water variables?
But not the water variables, yes. So that is cloud cover and not convection. So it's significantly, and that was going to be my transition in 2 slides, but it's much easier than other types of parameterization because it's mostly diagnostic and then helps for radiation macrophysics, but it's not like convection where if you get it a bit wrong, your whole model blows up. But we work on convection a lot because it's very challenging, but it's a lot more efforts and things can go wrong a lot more intensely than with cloud cover, which is it's not easy, but it's relatively much easier. But the ICON team, I'm very lucky to work with at the DLR, was able to put it back into ICON, recalibrate the model against observations, and unlike neural network, because this only has 10 parameters, you can recalibrate in a much more, I would say, almost naive way. It's not naive because it's still based on progressively longer rollout, but I'll get to, for example, what Klima does in a second. You would argue it's more naive than like some of the really nice machinery that has been developed for calibration by other groups. And if you retune that discovered equation with the other parameterization, you get it's much easier to be closer to observations than with the previous parameterization, which was Sundqvist. So we get 2% closer, almost 2% closer to observations in terms of cloud cover. And then for top of the atmosphere shortwave fluxes, we also get 2 watt per meter square closer. So it's not solved by any means because until you replace the convection, you won't have as much of the benefits that machine learning could offer, but it's much easier to go closer to observation than more traditional parameterization. So that's one of the biggest end-to-end success we've had over the year developing machine learning parameterizations. Okay, but that's the exact question you asked. What about these harder variables? And then I want to give a shout out to the efforts. So I was lucky to work a bit with, it was a work led by one of Tapio's grad student who's still there, Costa Christopoulos. And for processes like convection that are harder to directly observe but have such a big influence, you closer to an inverse problem where you can observe the resulting climate, but you don't necessarily observe or have a quick access to the process itself. And in that case, and I guess, Tapio, you're going to talk more about it? Okay. The calibrate, there's a lot of efforts that are all, that were formalized in this calibrate, emulate, sample pipeline, but now, I mean, there's been so much improvement since then that are based on ensemble Kalman inversion, which is nice because you don't need to differentiate the model. So even if you're working with an older school model that cannot be directly differentiated, what you can do is you can take your parametrization, make a guess at the parameters, run it, and then by comparing the resulting statistics with the reference ones. So in that case, it's LES, but now I think Lima also can calibrate against RF5, et cetera. The pipeline has been really improved. You can inverse and recover and improve the parameters. The nice thing is that this is done in a Bayesian way. So you also get uncertainty estimates for each of these parameters. And the pipeline was sophisticated enough that you could train a shallow neural, very, very shallow neural network with 100 parameters using this pipeline. And there's a bunch of advantages because it's all built end-to-end and you directly optimize on the conditional climate statistics rather than the tendencies of the parametrizations themselves. The resulting hybrid model is stable. Now, I do want to say there's no free lunch. There's always a challenge. So what you do in that case is you move a lot of your problems earlier. So in model development, there's always bugs. I don't think anyone can develop a model without figuring out bugs yet. And basically, the bugs are moved up front, which means your model will crash during training rather than after training. So basically, you see your bugs earlier. So it just moves where the bug appears. Because in traditional, yeah.
Just we're at Q&A time, but there's been questions and stuff, so a few minutes to wrap up.
Okay. Okay, so I'm gonna skip over like an experimental alternative we developed if you don't have a sophisticated inversion pipeline and you're working on convection. Recently, we came up with a fun way where, I don't know if you know, but AlphaFold has this confidence loss where you can, actually it's one of the best training trick that I've ever learned with neural network. You predict your own loss. It helps you converge faster, and on top of that, the uncertainty estimate that comes out of it is really good. And we've developed an experimental model where we mix a traditional parametrization, TITKE, with a machine learned one, and it's transfer learning because we didn't have the right icon training data set at the time. And then based on the confidence loss, you say, I'm going to put this much on the traditional parametrization and this much on the other one, and you can calibrate that. And so it's only a few parameters, and you can calibrate that to observations directly. So that's a new strategy if you don't have a sophisticated calibration pipeline. The slides, the links, the paper links are on the slides, and this was a preprint Helge Hoyer et al. And this is experimental and currently being peer-reviewed. So test it at your own risk, but it's really nice. We test the physics-informed loss. We stabilize the parametrization by using additive noise, which is like a follow-up from work I did with Noah like way years ago. Now it's formalized with the ingression framework by statisticians, and you can do it during training rather than after. And then we use that learned confidence to linearly mix two precipitation, calibrate it with observation, and we get really close to GPCP, and we get rid of the double ITCZ bias. So it's a bit experimental, it's imperfect, but I really enjoyed doing it because it's taking the best of both parametrization, and you can even learn you can even look at the partial dependence plot to see what it took from both, like which dependent of the column, water vapor, etc. That's why I'm so intrigued by this idea of mixture of experts, where maybe there's no single best model, and you can just learn how to weight different models. And so AI models may be good at some things, and maybe traditional models are better in extremes we've never seen on Mars. I don't know. And then you mix both. You just know you need something to be able to mix them, though. And that rule, in our case, is a confidence loss. So it's the neural, it's a machine learning estimate in its own error, which we found was quite reliable. And when it starts saying, okay, my loss is way too large, we switch back to the traditional parameterization, which is similar to some of the work you do with the one class SVM, except it's generalized with the confidence loss. Okay, and Adam, can I make my one experimental argument? Okay, this is something I did while writing the review. A few people looked at it. It's by no means perfect, but I wanted to get an idea of the scaling of the AI climate models out there. And so I have tabular data. It's open. I can share it with anyone who wants. I have the reference with which paper I took it from, etc. And so I looked at the simulated year per wall clock day, and I divided it by the number of accelerator. It's really just the number of GPU cores minus the neural GCM, which is the number of GPUs. And the number of prognostic variables. And then you plot it against horizontal grid spacing, and then it makes it look like AI models are more efficient. But then you say, okay, if you're a bit of a skeptic, which I am, you say, okay, but are they really more efficient if I take into account the number of vertical levels and then the time step? And so, a really naive scaling tells you that this is a measure of effective complexity of a climate model. So number of prognostic variables time number of vertical levels divided by spatiotemporal resolution. Mean spatiotemporal resolution, right? Because they all use different grids. And then once you do that, they all fall on the same line. And here I have different models. I have AI climate model emulators, hybrid models, including Klima. Tapio, I did not use the latest numbers you guys sent me, so take that with a grain of salt. I think the latest numbers are a bit better, so this will be updated in time. Ignacio from Google sent me the downscale, the number for the downscaling models. It's a bit more complex to measure this, so Ignacio made a bunch of assumptions and put them in there. And then instead of comparing them to traditional climate model, I'm taking the GPU-ported climate models, which I think is a much better reference point. And once you do that, so that's GPU-ported Scream and Icon, yeah. In Switzerland, people love porting models to GPU. It's a passion. I don't know why, but it's like everyone does it, even in solid or science. And so once you put them all, they mostly fall on the same line. Now, the conclusion is not necessarily that, okay, it was all hype, but yeah, they're not intrinsically, AI models are not intrinsically more efficient, with the caveat that first, they weren't as optimized, right? They didn't have as many years to be as optimized as a GPU-ported model. But then there's a big, interesting point, is that for traditional numerical models, sorry, here we're more thinking of climate than weather, you need to go much higher in resolution than what you actually resolve. So for instance, you could have discrepancy factors as large as 4 or 5 between what the nominal resolution and the effective resolution. I'm not an expert on that. There's a really nice paper by Claver et al. In 2020. Whereas AI models can directly target the resolution you want as long as you provide the right data set. And I think that's where they're the most impressive. And you can destroy this. My goal is it's never going to be perfectly apple to apple, but my guess is to show this plot eventually in the survey just to have at least one clean plot where you can say, okay, are AI climate models really more efficient or not? Yeah.
Yeah, one little comment around that. I think that's absolutely true. They are actually very similar in terms of performance. The main thing you get with the AI models is that you're not under the CFL conditions anymore.
Correct. That's exactly the point. Because you can directly target the resolution you want. You don't have to worry about CFL, and you don't have to worry about effective resolution. So
right. But that's huge, right? You can start looking non-linearities and much faster.
Yeah, because
still CFL. There's nothing.
We can debate that.
The reason the AI models allow you to take longer time step is that they allow you to take a much wider stencil. If you take a wider stencil, of course, your CFL bounds move.
Right, so it's like infinite CFL, basically. Yeah.
Well, if you do the whole globe in one go, yes, but as soon as you like to go to higher resolution, you can't do that either.
I would argue, I'd love to discuss that. I would argue
no.
otherwise.
It's a big debate, but like if you look at high resolution, we don't really have any AI model except Klima, which is a hybrid, right? So there's also like, we don't have data points here. So there's also like, the question is still there. I mean, maybe Noah has data points there.
No. I mean, maybe we should. I mean, but what's this like number of grid points time? You know, the number of scalars is this n prog times n lev over delta x squared. So like, what evidence do you have that the number of scalars is a good measure of model complexity? That seems to be like the main takeaway of this slide. I mean, because you're kind of does that, yeah.
I don't have strong evidence. Just if you use that, then things roughly fall on that line. I'm not making strong argument. I've just collected the data that I could, and I've plotted it to understand, you know, if you look at this, then it's clear that if all you care is horizontal grid spacing, for example, regardless of vertical levels and the time step, which, you know, time step you could care or not. It's sometimes more of a constraint than something you care about. The AI climate model emulators are more efficient. Here it just gives you preliminary numbers. I don't want to make too. I'm not confident in how each of these is going to be also on different hardware, right? So there's so many asterisks to this.
I like where you're going with this.
Yeah, it's just really hard. Yeah. And actually, I thought you would be the most skeptical of the room, so I wanted
I mean, just as you refine delta x, obviously you're not really adding more. If you're refining a blurry field at increased resolution in space and time, you're not really adding more information. So it's not exactly like, you know, apples to apples. But I think something like what you're getting at is apples to apples. Like,
I mean, also like, I'm not going to point to any model in particular because it's going to create controversy, but like it could be that one of these models is really bad, right? It's not because like you could have a model that's very fast and terrible, right? So this is, and here I have no measure of performance. So if I have a super blurry model, it would look very efficient. It would look nice on that plot, but you wouldn't want to use it. So that's why there's that. The other hardware is a big caveat. I think what's important is to list all the caveats and then yeah.
Actually, I think one thing that would be awesome to see on this plot is to also see the match between where the spectral resolution drops. So you could have like a sense of what's the actual effective resolution of the model.
But then I need to collect spectra for all of these models, which I can't do, I think.
Okay,
maybe we can help. Maybe we can help.
I'm basically getting numbers from people and from papers. Because I mean, it's not like my lab has the capacity to run these, right? So this is, but maybe people who have more compute could try to go a bit further with it. Yeah.
Yeah, one question maybe moving beyond this plot. I appreciate you trying to differentiate AI for weather and for climate, because as you alluded to, they're super different.
Yeah.
I wonder if I can ask you kind of a higher level question on that, which is, I think they're also very different in what your end of the day goals are. And I think even within the AI climate space, people often have very different goals and that leads to different approaches. So I wonder if you can comment on for you what you think the most important goal for AI plus climate is. And then the sub question, as you talked about that, like emulator versus kind of replacing parameterization approaches. And those are pretty different. Yeah. So what are your thoughts for like which one of those is most promising as we move forward?
Okay, these are really good questions. I don't know that I have good answers. For the first one, I'm really fascinated by this idea of counterfactuals. So a good climate models, as long as the boundary conditions in greenhouse gas, aerosol, land, water use, etc., you give are not absurd, I'm really interested in the model being able to produce a transient, so time resolved, and even ideally very spatially resolved climate state in response to any reasonable boundary conditions. And so there's this causality aspect where maybe a country we've never heard of starts emitting like a peak aerosol right there. And for me, a good climate model, including an AI one, should be able to give you a proper transient response. For me, it's interesting because it's a really hard test, I think, for current data-driven climate models. So I think until we get there, There's some really cool work from Mila, for example, with Julien Broussard, like in the latent space, where they try to enforce some kind of causality. But until we get there, I think we're not going to put enough efforts in causal machine learning, which I think we ought to put a bit more, even if that field can be a bit difficult. And it also underlines the role of physics in helping us generalize to situations we've never seen. So for me, the counterfactual is the most interesting challenge. That's for question 1. For question 2, I think right now I've been kind of taking the Switzerland approach of looking at different groups doing different things, and just I'm genuinely curious, and I don't want to bet on one strategy or the other. What I want to point out, though, is that AI climate model emulation and hybrid AI physics modeling are still subgroups of all the categories that are being explored, and I think these 2 subgroups are quite promising for the counterfactual response problem, because a lot of other strategies that are more brute force AI don't really think about scenarios we've never seen, and usually at best they'll maybe interpolate between scenarios they've already been trained on, for example, if they train on CMIP6. So, I don't know, I hope that was satisfactory.